Good afternoon. Last class we saw the implementation of finite state machine. Once we are given a state graph which represents a finite state machine, we can draw the state table. From state table we draw the excitation table. Then from there we get the equations for inputs to the flip-flops that we use in the machine, and we can also get the output using the state table or excitation table. So, we have seen a lot in the last few lectures, starting from finite state counters, for example, is a finite state machine without any input, or counters with input for up or down, or any type of state machine represented by a state graph where there is an input x and an output z. All that we saw. The most important link is counter is a fairly simple problem. So, it starts from 0 and goes to whatever the final count and goes back. What we saw in the last lecture, we took a state machine whose state table is given to you with an input and output. We also saw two variations. One is called the Moore machine and the other is called the Mealy machine. But the important question which we have not addressed so far is how do we get the state graph for a arbitrarily defined problem sequential circuit. So, any synchronous sequential circuit we should be able to draw a state graph, and from there the rest of the things are simple. State graph to state table to excitation table to flip-flop input equations and so forth. Now, today we will see how to draw the state graph for a given problem. So, the steps in the design of finite state machine. Statement of the problem. State graph. Once you give a state graph, you have to see whether this is the minimum state graph or the number of states, is it minimum for this or can it be reduced further. A reduction of state graph is called actually reduction comes after we draw the state table. See, state graph to state table to reduction will to the final. So, once we draw the state graph, given the state graph, we write the state table, see if it can be reduced, then we write the final state table. So, I do not know which, this can be put here and here, but again we have to do the state table. So, it does not matter which order you do. 5. From state table, minimum state table, we draw the excitation table which uses flip-flop excitation depending on the type of flip-flop. this is JK, D, whatever. From there we get flip-flop input equations, inputs, then the circuit. Circuit consists of both combinational and flip-flops. We started with the state graph which is regular, like a counter. From there we were able to design the machine using state table and flip-flops. Then last class we saw the counter which is non-sequential. That also we saw how to do that. Then we saw last lecture, given a state graph with input output, given a state graph with an input output and the number of states defined, you know how to do it because you know how to write the state table, and from there how to get the excitation table and so forth. So the only step we have not seen so far here is how do you convert a given problem statement into a state graph. That will be the focus of today's lecture. You are given a statement of the problem, you have to draw the state graph. That is the most critical step in the design. Once you have a state graph, everything else is a mechanical procedure. Once you have the state graph, you know how to draw the state table. From there you know how to get the excitation table depending on the type of flip-flop. Then you know how to get the flip-flop inputs, and then you can draw the circuit which consists of both sequential flip-flops. I mean both combinational logic and flip-flops. So today we will see this. This is most important. Given a problem, how do you convert it into state graph? But there you have an additional step which is not seen earlier. Because we draw the state graph, earlier so far we have been given state graphs and all you have to do is write the state table and proceed. Now since we are going to develop the state graph, there is no guarantee that it is a minimum state graph. So I will go through this step also. First I get the problem, write the state graph, and then see if it is a minimum state graph possible. If it is not, reduce it to the minimum possible state graph, and then do the rest of things. These are all steps which have been seen, also very fairly mechanical. But this is the design of state graph. This is the most important or critical step. And because of that, this also becomes important. So let us take a simple example. I have a finite state machine. The moment I draw a finite state machine, we have to assume that it has both combination logic to drive flip-flops, flip-flop inputs. are driven by combination logic, and the flip-flops. So, this consists of both combination logic to excite the flip-flops and the flip-flops themselves. That is understood. Now, this particular example I am going to discuss is going to be a very simple example. As always, we start with a simple example and then develop. Only then you understand it properly. The input is a variable called x, output is a variable called z or z, whatever you want to say, and then I have to feed the clock to this. First I will describe it words. What is it supposed to be done by the FSM? What is the object of this FSM? What is the function of this FSM? That is called a problem statement. So what is going to do is, there is a x input comes serially along with clock. That is one change in x per clock cycle. Z is output. This incidentally is a pattern detector. So it examines, circuit examines x and gives output z. If the pattern (101), if a pattern 101 is detected, z should be 1, otherwise it should be 0. I will give an example what I mean by this. I have a pattern x which is serial pattern 1 1 0 0 1 1 1 0 3 1 0 1 1 1 1 1 0 1 1 0 I can write anything, does not matter. So as the clock goes, as a function of time, I get 1 bit at x, I keep giving 1 bit at a time, 1 bit per every clock cycle into the machine, which has this pattern. This pattern is not a unique pattern. You can talk of any pattern. Something like identifying the password. Suppose you have a combination lock at home. You have to have a particular combination before it opens. It can be done electronically also. What we normally do in these locks we buy, you have to set the thumb wheels to a particular pattern for it to open. But electronically I can also do it. I can keep punching, and when I get the correct, hit the correct sequence, the lock will open. Something like that. So this is not a unique pattern, that's what I am trying to say. Output should be whenever there is a 101. There is a 101 here. There is another 101. Oh, I did it arbitrarily, it has come. So whenever this 101 comes, I should have an output 0, 1, along with the last bit. Along with the last one, 101, along with the second one, I should get an output 1. So it should be normally 0. Until I get this 101 pattern, I get an output 1, and then I have 0, 0, I get output 1, then I get 0, 0, I get output 1, then I get 0, 0, 0, 0, output 1, and so forth. So given this test pattern, given this input sequence, which is not fixed, once you design circuit should work for any input sequence, but the only thing it should work for is whenever 101 is found out in the pattern we are given the input, the output should be 1 corresponding to this third bit, which is the second one. Along with the second one, which are the third bit, I should get an output 1. Rest of the time the output should be 0. That is a simple problem. Now, how do you go about this? We have to draw the state graph. Once you got this problem statement is over. Now I should draw the state graph and see whether there is a minimum. Let me draw the state graph. Let us say the circuit is in state S0. S0 is reset state, nothing happens there. The circuit is not turned on, it remains in S0. At S0, when the circuit is in S0, two things are possible. I can get a 0 or I can get a 1 input. So if the input is 0, there is no point in taking any action. You know this last class I did this. You draw x stroke z. When x is 0, z is also 0 here. So circuit remains as long as the input is 0, the input pattern is 0, 0, 0, 0, 0, 0, 0, 0, nothing is going to happen, it is going to remain in the reset state. Moment the 1 comes, it has to go to another state because we have detected a 1. This 1 can be a part of a 101, need not be. After 1 it can again go to 1, 1, 1, 1, 1, does not matter. Since the first one is identified, it is possible that this one can be the start of the next sequence 101. So it remains here. So S1 state corresponds to input 1. In S1 state, if 0 comes, it has to remain here. Because now if you put a 0 here, if a 0 is detected, it should go to another state. Let us call it S2. Because a 0 is detected, it could be 101 or it could be 1000. We do not know that. 1 and 0 are 2 bits which are part of this sequence I am detecting. So because of that, I should go to a new state called S2, which tells you had a 1 and a 0. No output yet. But if it is 1 here, it keeps in this state. As long as 1 keeps coming, I will be in 1. The last one will be counted. Then this 0, 0. Now if a 1 occurs here, I will have an output of 1. Now because why do you go back to S1? Because this is a 1 and this 1 could be part of the first next. For example, this 101, supposing it is 10101. This is one pattern, this is another pattern. So this one could be common, the end of this pattern or the beginning of this pattern. So because of that I should go back here. On the other hand, if it is 0, it goes here because 101 now it will become 100. If it is not a 1, 100, no meaning, only 0 is there. So it is 0, 0. This is the state graph. How do you draw it? I explained to you. You have to think of each possibility. First start with the research state. At each state you see what will happen if x is 0 or what will happen when x is 1. If we can go to one of the existing states, you go, otherwise you start a new state. For example, again one more time I will explain. You are in a state as 0, nothing happens. As long as 0 comes, because my pattern is 101. Without 101 I can't have any output. So as long as 0 is there, nothing is going to happen. Zeros keep coming. If a 1 comes, you go to another state because it could be the start of a pattern. And if it is a 1 here, again it is 1, 1, no meaning, but then that 1 can be taken. So you keep here. If on the other hand from here, if it is 0, you go here because now it will 1, 0 already, 1, 0. And at this state if you get a 1, then become 101. Output is 1. Why do you go back here? Because this could be, as I said, 101 has been detected, but this one could be the starting of a next pattern, this overlapping pattern. On the other hand, at S2, if it is 0, there is no point because already it is 1, 0 and then followed by 0, 0, 0, 0. Nothing is going to happen, so go back here. Now this is the state graph from a given problem statement. Whether it is the simplest possible state, I should draw the state table. It looks like it is the simplest because there are only 3 states. Anyway, we will go through that exercise. So, this is state graph. State table will be, at state table you do not say A, B, you only say S0, S1, S2. The present state, next state, output. This is a Mealy model. Mealy machine means the circuit is in a particular state, output is determined by that state as well as input. More machine means within the state the output is defined. Output is given for states. It will say S0, at S0 it will have 0 output, S1 is 0 output, S2 is 1 output, it is called Mealy machine, Moore machine. In Mealy machine, circuit is in S, for example, if you take here, circuit is in S2, a 1 occurs, then the output should be 1. The circuit, which state it is and what is the input together, they decide the output. That is a Mealy model. So, this is a Mealy machine. So, we will say present state, next state when x is equal to 0, x is equal to 1, output when x is equal to 0, x is equal to 1, present state is S0, next state is S0 if x is 0, S1 if x is 1, output is 0 in both cases. Next is S1, in S1 state, if it is 0, it goes to S2, if it is 1, it remains in S1, both times the output is 0, S2, if the input is 0, it goes to S0, if it is 1, it goes to S1, output is 0 if x's input is 0, output is 1 if in S2 input is 1. This is state table. I am not going to tell you how to reduce this. Later I am going to take a more complex example where reduction is possible. This is a trivial case. I always start with a simple example for you to understand and then develop further. So, it's a trivial example, only 3 states, we have to detect a pattern of 3 bits. I do not think it is going to be smaller than this. There is going to be no reduction state. So, let us not see what a state reduction means at this point. We will assume this is the final state table. So, next step is to give values for S0, S1, S2. There are 3 states, so we need 2 flip-flops. We will call the flip-flops A, B, 0, 0, 0, 1, 1, 0. So, the excitation table is where you use, instead of S's, you use zeros and ones. Excitation table, present state, input, next state, output, this is AB, input is X, next state is A plus B plus. I told you why we wrote A plus B plus, because the same A and B, but to understand that is next state variable A and B rather than this state variable A and B, we put a plus. There is nothing like A plus state. Same A as an output, at this point in time it is A, then you give the input, next input and the input present state variable, then it goes to the next state which is again A. So, A going to A, sort of confusing, so A goes to A plus we say. Otherwise A plus or B plus has no meaning. Now output is Z. Now I said AB is 0 0, X 0, 0 1, 0 0, X is 1. This is for S 0. S1 0 1, input 0, 0 1, input 1. S1 S2 1 0. So if the present state is S0, X is 0, it goes again to S0 and output is 0. The present state is S0, X is 1, it goes to next state S1, which is 0 1. Output is 0. So we have taken care of S0 state. S1, if the present state is S1, input is 0, it goes to S2, which is 1 0. The present state is S1 and the input is 1, it remains in S1. Both cases the output is 0. Now, present state is 1 0. If X is 0, it goes to S0, which is 0 0. If it is 1, goes to 1, 0 1, and output is 1. This is the excitation table. Excitation table is nothing but a state table in which you give variables A, B, C. Whereas in state table you use S0, S1, S2 symbols. Now I can implement this using any type of flip-flop. We know how to do it using T flip-flop. We know how to do it using JK flip-flop. So we will use JK flip-flop. For using JK flip-flop, I need to know the excitation equations for JK, the excitation table for all. Many of you have missed several lectures because of college closure. I have been doing a lot of things in this period. So you have to go through the material which is in the website, as well as the NPTEL lectures. Go through NPTEL lectures, go through what I have done in the last few classes where you have not been here, then only you will follow this. I cannot repeat everything now, but fortunately they are all in the website as a recorded lecture. They have put every lecture, including the last lecture which is delivered on last Wednesday or last Monday. So unless you see them, you will not be able to appreciate some of these things I am talking about. For excitation table, what is the JK flip-flop excitation, what is the D flip-flop, all that I have done. T flip-flop, we have done several examples of sequential circuit, counters, sequential counters, arbitrary counters, up counter, down counter, with input, excitation table, all that we have seen. So you should spend your time doing that. So excitation table for JK, Q to Q bar, Q to Q plus. What is J, what is K? 0 to 0, 0 to 1, 1 to 0, 1 to 1. It is 0 don't care, 1 don't care 1, don't care 0. Without this you cannot proceed further in this problem if I am using JK. If I am using D flip-flop, it is very simple. My A plus same as D. So what I need next state is what you give as input D. JK flip-flop is slightly different, so that is why I am going to take it. Now that means I should also draw now JA, KA inputs for A flip flop, JB, KB inputs for B flip flop. Now to see first A here and A plus here, and use this table to see what should be JA and what should be KA for this transition from 0 to 0, 0 to 0, 0 to 1, 0 to 0, 1 to 0, 1 to 1, 1 to 0 to happen. What input I should give it J, what input I should give it K. That will be done using the excitation table. We will quickly do that. 0 to 0, if 0 don't care. This also 0 to 0. Then this is 0 to 1, 1 don't care, 0 to 0, 0 don't care, 1 to 0, don't care 1, 1 to 0 again, don't care 1. JB, KB, I should use the present value of B and next value of B. Then I will get JB, KB. Again 0 to 0 is 0 don't care. 0 to 0, 0 to 1 is 1 don't care. 1 to 0, don't care 1. 1 to 1, don't care 0. 0 to 0, 0 don't care. 0 to 1, 1 don't care. That completes my excitation table for the flip flops. I do corner maps for JA, KA, JB, KB and Z. My design is completed. Quickly let us do that. KA, inputs are A, B, X. KA, we only have 6 0 0 0 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 because there are only 3 states. So S3, if we have one more state S3 with 1 1, I will have 2 more terms, but they are not there, so we can put don't cares there. So now it is, you draw this here, map it here, JA is 0, 0, 1, 0, don't care, I don't have anything here, so I will also put here don't care. KA would be These are two ones, and these two are don't care because there is no such state. This is nothing but JA is nothing but Bx bar. Ka is nothing but 1 because all of them are, all don't care can be interpreted as 1, so Ka is 1. This is for JB, second flip flop. This is for KB. Use this here values 0, 1, don't care, don't care. 0, 1, don't care because this last two is not available. Only 3 states. We have only 6 terms here. If you have 8 terms, this 3 input variable corner map has 8 cells. So whatever cell is not there, you can put don't care. Similarly here, don't care 1, 0. So JB is nothing but this, which is X. KB is nothing but X bar. I want to finish the whole exercise here, but I don't have a space. I will draw the circuit separately. I also have to draw the Z. Z is nothing but last row, which is A bar, A, B bar, X. So Z is there's only one entry in the Z. That corresponds to that one entry. A is 1, B is 1, X is 1. A is 1, B is 0, X is 1. So Z is nothing but AB bar X. So I have to draw this. I'll use this place. So I have 2 flip flops, and I have chosen to use JK flip flops. That's all. The circuit is going to be so simple. There's a JK flip flop 1, which is called A flip flop. JA, KA. This is A bar. JB, KB, JB, KB, Q bar. This will be B, this will be B bar. So what is my JA? Bx bar. B is already there. So Bx bar. X is the input. So which is needed as a Bx bar now. This is X bar. So here Bx bar. B comes from here. I am not going to draw all that because it will become a cluttered map, a circuit. So this B becomes here. So I don't want to go on drawing lines like this, then it will be so confusing. Lot of lines and lot of crossings, it's a cluttering. So I leave it here. X is available, X bar has to be gotten, A bar, B bar are available, no problem. Ka is 1, so no problem. 1 is 5 volts or whatever higher voltage you have. JB is X. KB bar, X bar, which is already there. X bar is there, I can use it. And Z is A B bar X. A is available, B bar is available, X is available. This completes the circuit design for detecting a pattern of 101. So you have a series of bits coming at the rate of 1 bit per clock serially. Serial bits are coming at a stream with 1 bit per clock. Whenever a 101 occurs, corresponding to 101, the second one, not the first one, 101, the third bit or the second one, output should be 1. All other times output is 0. So we have Z is 0. Normally, when a 101 is detected, output 1 occurs. So this is a simple example, but it explains everything. Drawing the statement of the problem and from there drawing the state graph. Reduction I did not do it because there is no reduction, there are only 3 states. From there I draw the state table where I use SS, S0, S1, S2, etc. And then I put excitation table because by the time I should have decided what type of flip flop I am going to use. Since I was going to use JK flip flop, now S0, S1, S2 are replaced by AB 0, 0, 0, 1, 1, 0. And then I draw the flip flop inputs using the excitation table of the flip flop, chosen flip flop which is JK. So I have corner map for JA, KA, JB, KB and Z and draw the circuit. This is complete except one small thing. The design is complete except for one step, one missing thing. What is that? Anyone? Only one small thing is missing. What is that is missing in the circuit? Please. Nobody knows? Anybody who has put your hand like this? There is no point in sitting through without understanding these basic things. Please. Somebody. Clock is missing from here. Without clock, how can a sequential circuit work? Why can't you think of that? Do we have a clock in this circuit? No. Unless you show clock, this has no meaning because I told you as X comes 1 bit per every clock cycle. All sequence circuits should have clock. You have not talked about it, I have not thought about it, you did not. Did you? Did someone know but did not answer? Please tell me. Just raise your hand. Somebody knew but did not answer. Anyone? Yeah, you see, why can't you talk? Huh? Why can't you talk, man? Okay, next time I ask a question, you can talk. So the clock has to be drawn. Okay. So this is how, this is the most, this is one comprehensive coverage of sequence circuit design. Finite state machine or sequence circuit, whatever you want to call it, using flip-flops and combination logic. You draw the state graph, you get the state graph from the problem statement, draw it, see if it is a minimum state table, assume state graph, reduce it, get the binary, I mean the change the states into variables, and then decide on the flip-flops you use, draw the excitation table, do the corner mapping, get the circuit. This is the simplest possible way, and I explain so many things. I am going to take one more example. I do not think I will be able to complete it. First two steps are very important. I am going to do that. Problem statement, drawing the state graph, and even reduction I will do. The rest of it you can do. Once you have a reduction, the number of states is given, then to put them 0, 0, 0, 0, 0, 1 and all that I do not have to tell you. And then you can decide to use either JK flip-flop or D flip-flop. Okay. Second problem or second example today. Example 2 is again a pattern detector, but a little more complex. There is a bit stream again, one input, one output, FSM, which consists of flip-flops and combination logic. A one input X, one output Z, and the clock. Again a pattern detector. This pattern is, I have two patterns in mind, 0, 1, 0, 1, 1, 0. Whenever the pattern 0, 1, 1, 0 or 1, 0, 1, either of them, any one occurring, I should get a 1. So again X will be a series of bits, 1 bit per clock cycle serially coming, serial bit stream with 1 bit per clock, and whenever you find this pattern or this pattern corresponding to the last bit of this pattern, whenever you find this or the last bit of this pattern, you should get Z is equal to 1. Rest of the time Z should be 0. That is the problem statement. One more thing I should tell you, like last time, if it is 1, 0, 1, 0, 1, last time we detected, this is one pattern, this is another pattern. They can be overlapping. If the overlapping also you should find it. So if 1, 0, 1, for example, take this example, 0, 1, 1, 0, 1, blah, blah, blah. Now 0, 1, 1, 0 will have an output of 1, and 1, 0, 1 we will have another output of 1. This is what I mean by overlapping pattern. Now the problem is to get the state graph. Once you have the state graph and simplify it to minimum, rest of the steps are mechanical. I don't have to do it again and again and again because I have been solving this type of flip-flop based solutions for so many classes, so many examples, there's no point in keeping on doing it. You should know by yourself. By now you should know how to do it by yourself. So let us look at the point. Now, we will always start with S0 as a reset state. Again say milli machine. That means output is dependent on the input and the state from which it is coming. Moore machine means output defined by the state. Now S0 reset state. If 0 occurs, it could be the start of this pattern 0 1 1 0. So I should start a new pattern, new state S1. S1 is detect as 0. If a 1 occurs here, it should be the start of 101. It could be the start of 101. So again we put a new state S2. Whether you need a new state or go to one of the existing states decides will be depending on whether this 0 comes or 1 comes. Can it go to one of the existing states or you don't have a state, so you will have to start a new state. S2 is detecting 1. Output is all, I will have to draw like this. X. X is the input, Z is the output. Milli machine. Moore machine will not have this stroke. Moore machine will write the inputs only here, output will be within the box, within the circle. Then from here, if a 0 occurs, I keep here thinking that it could be the next 0 can be the starting of the next 0 can be the starting pattern, next 0 can be the starting pattern. I keep thinking it is every time a 0 comes, first bit of this. If a 1 comes here, I will go to a new state, S2, S3. S3 is already I have found out 0 and a 1. Here it is 0, here it is 1, so 0, 1, which is nicely the first 2 characters of the pattern that we want. On the other hand, if here S2, if a 1 comes, you stay here because this could be the starting point again. Any new one start, if it is 0, you go to a new state called S4. S4 will tell you 1 0 has occurred. Why can't we go here? From here you can go here, but then we already registered a 1. From S2 we can go to S1 because this is 0, but then we would have lost the 1 that we already got. So we didn't want to go to S1. We can't go to S2 because this is 0 1. I don't want 0 1. So I need a new state, S4. S3 what happens? In S3 if a 0 comes, because already we have 0 1, If a 0 comes, this cannot be this pattern now because 0 1 1 0 is this pattern. Already I got 0 1, but then I don't want a 0 here, but it could be this 1 0. So if S3 0 comes, it could go to S4. Because this is 1 0, 0 comes, go to S4. Because S4 is 0 1, there's a 0, there's a 1. This is 1 0 1, so this is a 1, this is a 0, so it can go here. On the other hand, if 1 comes, it should be 0 1 1. New state called S5. S5 state tells you 0 1 1 has occurred, which is part of this pattern. 0 1 1. From S4 what happens? You know in S4, if a 1 comes, nothing can happen because this is a 1 1 0, and this 1 here will give you 1 0 1. That is what we want. 1 0 1. Get an output of 1. And this 1 can be a sort of a new pattern. So it gives an output of 1 and goes to S2, which is a 1 state. 1 1. Output will be there because it is 1 0 1 0 1, and this also can be the beginning of a next pattern 1 0 1. So it goes here back. S4, if 0 comes what? Already it is 1 0. 1 0 is 0, has no meaning. So it has to go back as if nothing has happened, only a 0 has come. S5, if a 1 occurs, would have completed the pattern. No. If S5 is 1 comes, S4 is 1 0, one. S4 is 1 0, S3 is 0 1, 1. 1 comes, it is not an output, we have got 0 1 1. We'll go 0 1 1 is already there, you know, S1, 0 1 1, S5. There another 1 comes, there is no meaning because 0 1 1 1 has no meaning, so this has to go back here. If a 0 comes, it goes to this place because this will be 1 1 0. Zero 1 1 and 0 will be there, give an output of 1. So we exhausted all the possibilities. You have to see how many, for each state, you should see what happens when input is 0, what happens is when input is 1. That is all you need to do. Just keep on doing it till we have now we have also taken both the patterns 0 1 1 from here to here, 1 1 0 no 1 0 1 from here to here, and 0 1 1 0 is from here. Now you draw this is state graph, then you write the state table. Present state, input, next state, let's say 0, what is the next state? Output. What is the output if x is 0? What is the output if x is 1? Now how many states have we got? S0 to S5. 6 states. S0, S1, S2, S3, S4, S5. S0, 0 takes it to S1, 1 takes it to S2, output 0, 0. S1, 0 takes it to S1, 1 takes it to S3, output is 0, 0. From S2, 0 takes it to S4, 1 remains in S2, output is 0, 0 again. S3, 0 takes it to S4, 1 takes it to S5. S4, 0 takes it to S1, 1 takes it to S2 with an output of 1. S5, 0 takes it to S4, 1 takes it to S2, the output is 1 here. This is the state table for the problem. If you are not sure of what happens here, it is confusing. You can add as many states as you want, but you have to go through this reduction process. The reduction process will eliminate the unwanted states automatically. In this case also there doesn't seem to be. How do you define an equivalent state? When a present state takes you to the next state, same next state for x is 0 and 1, and the outputs are same. So state SA is considered to be equivalent to SB if SA and SB go to same next states for each input if they produce same outputs for each input. Here there are only one input x, so x can be either 0 or 1. So, if any of these states leads to the same next state and the inputs are same, I mean outputs are same, then they are supposed to be equivalent. Let us say S0 and S1 know different next states. No two, this S1, S2, S0 has S1, S2 next states, S4 also S1, S2 next state, but this is 0, 1 output, this is 0, 0 output. Supposing this output is also 0, suppose this output was 0, then I would have said S4 and S0 are equivalent, there is only one state is required, other state can be eliminated. Unfortunately, we can't do that because outputs are different. So, from look of it, looking at it doesn't seem that these states are equivalent, but from looking you can't decide. So, we have to draw what is known as an implication table. Implication table will put all the states S1, S2, S3, S4, S5, S2, oh S0 is there, I forgot. S0, S1, S2, S3, S4. You draw something like a game. You draw this horizontal and vertical all the states, of course one less, because S1 will not be equal to 1 S1. So that you can leave. Now, looking at it, if there is possible, if you look at S0, is it possible that it is equal to S1? Yes, it is possible if S1 is of course there, S2 is equal to S3. If S0, if S1 is equal to if S2 is equal to S1, S3, then these two states are same. So I write here S1 becomes equal to S1 if S2 becomes equal to S3. Like that I finish this. S1, 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 S2. I don't know that this is right. Anyway, there is no possibility this is not there. S1 to S2 we have already seen. Oh, S0 to S, I'm sorry. S0 to S1, S0 to S1 if S2 is same as S3. S0 to S2 if S4, S1 is S4. S0 to S3 if S1 and S4 are same and S2 and S5 are same. We should have drawn a bigger thing. Anyway, it doesn't matter. S0 equal to S4 if it is not possible because outputs are different. So we put a cross. Since the outputs are different, there is not possible. Similarly, S0 to S5 is also not possible. Then take S1. S1 to S1, I don't know. I don't think we should have this. S2 to S1, S2 to S1, S1 to S2, S2 to S3, I think this starts here with S0. This one, 1, 2, 3, 4, 5. I don't know, something is wrong here because S2 to, you take S1 and S1 and S2 will be equal is S1 is equal to S4, S3 equal to S2. S1 and S2 we'll put here. S1 to S4 is S1 S4, S3 S2. S1 to S3, I mean S2 to S3, S1 to S2. So S1 to S3 will be S1 S4, S3 S5. S1 to S4 is not possible. S1 to S5 is also not possible. I think we should combine this. S1 is no point. S1 and S1 you don't compare. Similarly, S2 you take. S2 to S3, S2 to S2 not necessary. S2 to S3 would be if S4, S2 is equal to S5 and the other two are not possible. S2 to S4, then you take S3, S3 to S4, not possible. S3 to S3 you don't compare. S4 cannot be same with any state because of the output. and S5. Now, S4 cannot be equal to S0, S4 cannot be equal to S1, S4 cannot be equal to S2, cannot be equal to S3. Now, using this I can change this now. For example, you get S1 to S4 equivalent, not possible. S2 to S5 is not possible. S3 to S5 is not possible. This is also not possible. S2 to S3 is not possible, we have already proved here. So this cannot be. Since you have proved that S3 is not equal to S2, so no two states are equivalent. I could say this from looking at it, but this is the procedure. You can read a book for this. Roth gives you this. Roth Jr. gives you the procedure. So now, this is the minimum number of states possible, that is the second step, reduction and state graph. Now, after that I am not going to do, because we are going to have 3 states ABC, call it 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Then there we don't care. This is the state table. Decide on the type of flip-flops. Write the excitation table involving instead of SS using ABC. Use that information, and depending on the type of flip-flop, you write JH, KA, JB, KB, JC, KC, or DA, DB, DC, and then draw the circuit diagram. Then the design is complete. So, I want you to complete this exercise using D flip-flops to get the final circuit and JK flip-flop. 2 examples. So, last time itself I asked you to do something, I don't know, I don't remember. So, this state table I have given, there is a minimum state table. So, first step is taken care of, statement of the problem, second step is state graph, third step is taken care of, reduction, no more reduction possible. So, fourth step I already given you, state table. So, you are supposed to do only this much. Excitation table using the type of flip-flop, then flip-flop input equations using corner map, and then draw the circuit using combination logic and flip-flops. That is what you should do, so that we can move on. We have been spending a lot of time on sequence circuits, starting from latches to flip-flops, clock to flip-flops, edge triggering, level triggering, master slave. Then we went to counters, ripple counters, synchronous counters, up counter, down counter, decade counter, any arbitrary counting. Then we did as inputs, give inputs what happens to the sequence circuit, and then we did general sequential circuit design using input and output and this number of states, and Mealy machine, Moore machine. We have done several examples, and that will complete the sequence. Of course, we will do some more thing, an implementation point of view. But this problem you should be able to complete without any problem, without any difficulty. Okay, I will stop here.